Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We're delighted to welcome Matt Weinberg from MIT, who will tell us about algorithms for strategic agents.
Thanks. So thanks a lot for having me and coming to the talk. So, okay, so I want to talk about, so I don't know how many of you have seen this picture before, but this picture was shown to me in like my first undergraduate algorithms class. So what this is this is a Soviet railway map from 1955. And apparently the CIA asked early computer scientists to find a min cut in this graph because they wanted, in case they ever wanted to like disrupt the Russian supply flow. Okay. And now if we fast forward to 2014, this is a graph of what autonomous systems in the internet look like. And algorithms are run on this graph every second and to help route internet traffic. Okay. And so one difference between 60 years ago and today is that you'll notice that the graph on the left has less than 100 nodes and the graph on the right has 42,000 nodes. Okay, so obviously our algorithms need to be better and faster, but that's actually not what I'm going to talk about. And instead what I want to point out is that the graph on the left, all the nodes are controlled by one central authority. The nodes have no interests, and in some sense they just obey whatever the central authority says. Whereas in the graph on the right, there are 42,000 autonomous systems that are making their own decisions, and they have their own interests, and they behave in their best interests. So they're not just going to do what someone tells them to. Okay, so let me first give you an example to convince you that this is a real thing. This is not just like some crazy model. So in 2008, there was a faulty BGP table update that caused a worldwide YouTube outage. And so if you don't know, so BGP, is a protocol that is used to route all of our internet traffic. And so, so for several hours, 2/3 of the world was unable to watch cute videos of cats. And so what went wrong was there was offensive material on YouTube that prompted Pakistan to want to censor it. And so the Pakistani ISPs updated their BGP tables to map YouTube to nowhere. And the problem is that this was inadvertently broadcasted to the rest of the world as well. So the point of this, I think this is like a nice quote that summarizes what happened, was that nobody ran any viruses or worms or malicious code. This is just the way the internet works right now. So, no one was trying to take down YouTube, but it just happened because the ISPs were acting in their own interest instead of what the central goal of BGP was. Okay, so now I'm going to put this in a little bit of more of a general context. So normally when we think of algorithm design, we think of being given some input that you know, and asked to produce some output. And what happens in between is what we call the algorithm. Okay? So the model I'm trying to get at is called algorithmic mechanism design, where we have this extra step where you don't know the input, you're not given it, but you have to get it reported to you by agents who are strategic and have their own interests. And at the end, the agents experience some kind of payoff based on the output that you choose. So they actually care about the algorithm you run and what you choose to do. And so for this talk, I'm going to call this a mechanism instead of an algorithm to denote the difference. Okay. So in a seminal paper by Nissan and Ronen, they introduced this topic to the computer science community. And among other things, they posed this general question, which is how much more difficult are optimization problems on strategic input versus honest input? So how much harder is mechanism design than algorithm design? So the dream is we would love to have some kind of a black box reduction that says as long as you can solve algorithm design problems, you can also solve mechanism design problems and just throw it into this wrapper. So what I mean by that is what you really want to do is have some mechanism that works on strategic input. So it should take as input m different agents are going to report their input, and then it's going to produce some good output. And instead, what you have is just some algorithm that works on honest input. So it takes the input that's known and is correct in some sense, and then produces an output. And even more, we'd like to say that you just have black box access to it, which means you can't actually look inside. You can just probe it with inputs and see what it outputs. Okay, so what we'd love to be the case is that you can design this mechanism on the left with just black box access to an algorithm.
Is there one single output that's both what you want to do and what interacts with the agent's utility? Or are you allowed to have private output versus rewarding agents?
So for this talk, I'm going to say there's one output, and you have a goal in mind, and that goal would be the same if it was an algorithm problem or a mechanism problem. So for instance, maybe your goal is to make the agents as happy as possible, and it's not about doing something different for the different agents, but you want to find the outcome that makes all the agents as happy as possible, something like that. Did that answer?
Okay. So you don't have an output that's sort of predefined, or your own goals are predefined independent of what the agents want?
It could be, or it could depend on what the agents want. So as an example, let's say that I don't know. Let's say that I'm a government and I have some contract that I want to award, and everyone here is a business, and I just want to give the contract to the business that can benefit the most from it. Then what would be private information to all of you is how much you would benefit from it as a business, and that, based on how much you value it, would affect who I want to give the contract to. Does that? But my goal is to. Is that okay? Sorry. Okay. Okay. So let me say. So why would we want a black box reduction? And so one reason is that much more is known about algorithms than mechanisms. Okay. So one hope is that maybe we can reduce some unsolved problems in mechanism design to problems in algorithm design that are already solved. Okay. A second important thing is that the algorithms community is much larger than the algorithmic game theory community. So some kind of reduction like this would allow lots more people to contribute to mechanism design problems, and they wouldn't have to necessarily learn game theory to do it. Yeah, I guess that's arguable, but I'll say it's a plus. And the third is that hopefully this would provide a deeper understanding of mechanism design, because really we'd like to understand what makes incentives so difficult to deal with, both computationally and otherwise. Okay, and so what I'm going to show you through this talk is that with the right qualifications, some kind of reduction like this does exist. Okay. So I'm going to set up the problem, and then afterwards I'll describe like a series of papers that culminates in this result. Okay, so the setup, there's going to be some central designer, and there's going to be some agents, and there's going to be some possible outcomes that the designer is allowed to choose. And the agents are going to have a value for each possible outcome that kind of denotes how happy they are with that outcome. And I'm going to say that this information is stored in their type. So for the rest of the talk, just remember T stands for type. And T is going to be a function that takes as input an outcome and outputs that agent's value. Okay, so how happy they are. And also for the whole talk, we're going to be in a Bayesian setting, which is normal for economic applications. So each agent's type is going to be sampled independently from a distribution D. And every agent in the designer knows this distribution. Okay, so also for the rest of the talk, just remember D stands for distribution. Okay, so now the designer's goal is to decide some outcome, and this outcome should be feasible. So I'll give you some concrete examples later, but think of it as if I only have one item to give out, I should not be giving 7 people the item, right? If I only have one, I should be giving it to one person. And also, in addition to choosing an outcome, he's allowed to charge prices to the agents, and he has some objective function in mind that he wants to optimize. And this objective function, like I was saying, could depend on the types of the agents, and it can also depend on the prices that he charges, and it is also going to depend on the outcome he chooses. Okay, so before I give you examples, let me tell you the strategic aspect of the problem. So the designer first is going to design his mechanism. And a mechanism you should think of as just a function. So it takes as input a profile of types, so a report from every agent. It's going to output an outcome, and it's going to output a payment for each agent. Okay, after he designs his mechanism, he's going to ask the agents to report their types. And then he's going to choose whatever allocation he promised and charge whatever payments he promised.
What's a profile?
So a profile is a type for every agent. So like if there are 5 agents, it would be a type for bidder 1, 2, 3, 4, and 5. Yeah, sorry. Okay, so now each agent is going to decide what type they want to say, and they're going to do this based on the mechanism that they're playing, based on their beliefs about what everyone else is going to do, and based on this, they're going to report some type. And if they were honest, they would report their true type, but they're not, they're strategic. So instead of telling the truth, they're going to report whatever type happens to maximize their own utility. Okay, so if they think that they can gain based on the algorithm I'm running, if they think they can benefit by lying, then they're going to lie. So the designer's goal is to design a mechanism that first, it should encourage the agents to tell the truth. Okay, and the specific notion of truthfulness that we're going to use is called Bayesian incentive compatibility. What that means is that if everyone else is telling the truth, it's also in my best interest to tell the truth. So it's not as strong as dominant strategy, which means that it's best for me to tell the truth no matter what, but it is an equilibrium for everyone to tell the truth. And second, conditioned on being truthful, it should optimize his objective function subject to this. So maybe it's not possible to do as well as the best algorithm, but he should at least do as, right, so your target is of all truthful mechanisms, do as well as the best one. Okay? So that's the benchmark.
Sorry, you mean you optimize the objective function if you're in this particular equilibrium?
Yes, that's correct.
So, but there might be other equilibrium.
There may be other equilibrium, that's correct. Yes. Okay. So now I'm going to give you some examples to help ground this a little bit. So one example, let's say you're this nice guy and you have a bunch of gifts that you want to give to a bunch of kids. So you shouldn't be giving the same gift to more than one child, but it's okay for the same child to receive multiple gifts. And so you'd say that an outcome is feasible if it respects this. So it's feasible if it doesn't give the same item out more than once. And in this case, because you're just trying to make the kids as happy as possible, you want to maximize welfare. So as a function, that would look like summing over all agents their value for the outcome that gets chosen. So remember, Ti is the function that represents their value. So second example, maybe you sell houses. So you also should not be giving the same house to multiple agents. And also, you should not be giving the same agent multiple homes in this case. So in this case, you would say that an allocation is feasible if it's a matching of homes to agents. And because you're a salesman, you want to maximize your revenue. So in notation, what that would look like is you sum over all agents the payment that they make to you. As a last example, maybe you have to schedule jobs. And in this case, each job should be assigned to exactly one machine, but the same machine can process multiple jobs. You would say that an allocation, or I'll call it a schedule, is feasible if it respects this. And in this case, you want to minimize the Makespan, which is the processing time of the slowest machine, so the last machine to finish all the jobs it's processing. And so again, in notation, you'd be trying to minimize the maximum over all machines of their processing time.
The housing example,
Yeah.
Does an agent have not only tell you a type, but then do they have a accept or reject for the solution? You're going to charge them a payment and give them a good?
So the idea is that if the agent is truthful, then then the price that you give them for the house should always be less than what they're willing to pay for it. So they should have no interest.
Or
Say that again.
So you build that into.
Yes. Yes, that's true. So there's a condition. So part of truthfulness is a condition called individual rationality, which I didn't explicitly state, which means that it should be in every agent's interest to participate in the mechanism. So what would happen here is if you wound up giving them a price that was above what they wanted to pay, then it would not be rational for them to participate because they would rather just sit at home and not take the house. So yeah, that's good. I should have said that. And, but that is a condition that is imposed. But normally we think of that as being imposed by the truthfulness property rather than the feasibility constraints. Yeah. And that should hold for all the examples, not just the housing. And okay, so now I want to tell you what's already known about this. And so what we do know is that if your goal is to optimize welfare truthfully, no matter what kinds of types the agents have, you can do that as long as you know how to optimize welfare algorithmically. Okay? Now for revenue, I know there's some notation in this line that I'm going to define shortly. What we know for revenue is that for very simple bidder types, if you want to optimize revenue truthfully, you just need to be able to optimize virtual welfare algorithmically. And I'll say what these terms are now. So for types of bidders, what it means for a bidder to be additive is if it makes sense to say there are items, so like the gifts or the houses or the jobs, and bidder has a value for each item, and their value for a subset of items just sums their value for each item in the set. So there's really no interaction between values for different items. Okay? Single dimensional is a special case of additive where, as far as the bidders are concerned, all of the items are exactly the same. So think of additive as maybe like you have two items, one of them is a TV and the other one is a car. Then your value for a car and a TV is just your value for their sum. And single dimensional would be like you have 10 copies of the exact same TV for sale. Okay? And lastly, when I say maximize virtual welfare, for this talk, how you should interpret that is I'm just saying modify the input and then maximize welfare. So if you want to think of virtual welfare as welfare, that's fine, but just understand that the input is getting modified a little bit first. Okay? So that's what we know for welfare and revenue. However, for revenue beyond single dimensional settings, so for additive, we don't know anything. And what we'd really like is to be able to let the bidder types be arbitrary, and we really don't know anything there. And then also, as soon as you go beyond welfare and revenue, we really don't know anything. Okay? And in fact, the only thing we do know is an impossibility result that says that it's not possible to reduce truthfully optimizing any objective to algorithmically optimizing that same objective. And in particular, no reduction like this can possibly exist from minimizing Makespan. Okay? So what I'm going to show you in this talk is that moving beyond single-dimensional bidders, for additive bidders, and actually for arbitrary kinds of bidders, as long as you can optimize virtual welfare algorithmically, then you can optimize revenue truthfully. And for arbitrary objectives, as long as you can optimize O plus virtual welfare, so that same objective plus virtual welfare, then you can optimize that objective truthfully. And so this sidesteps the impossibility result because we changed the objective. Okay?
Welfare referring to that example you gave where you're just giving stuff out?
So welfare just refers to the objective of trying to make people as happy as possible. So it's not necessarily just you have stuff and you want to give it away. It could be like if I'm trying to build a bridge and I want to put it in the location that makes, the most sense for everyone. Something. But welfare just refers to the objective of my goal is to make everyone here happy.
So when you're saying this is doable condition that you can solve it algorithmically if there's no problem with agents telling the truth.
Yes, that's right. So what that means is that if it was possible for me to find the best location for the bridge, if I knew everyone's value, then it's also possible for me to design a mechanism that, accommodates the fact that you guys have your own interests and you may choose to lie, that will still wind up putting the bridge in the best location possible. Is that?
Right. Yeah, I'm trying to see from the examples how it could be that that second problem was not algorithmically easy.
So one example would be, so let's say, let me think real quick. So let's say that I was, instead of just giving away gifts, I was trying to, let's say that I was trying to run a spectrum auction. So the FCC, has this large radio band and they want to give it away. And there are these very complicated constraints on which spectrum can be allocated in which locations or something. So in some sense, it's a little bit like an independent set problem where, you have to make sure that wherever you allocate the spectrum, that it's not going to, does that make sense? Like if I allocate part of the spectrum here, I also can't allocate it anywhere too nearby. And independent set problems are hard to solve. Right? So there are problems where
Graph theoretic constraints.
Yes, that's right.
Things
Yeah.
that you can do that
Yes.
didn't appear in those simple examples.
Yes, that's right. Yeah.
When you say welfare is okay and refer to all these references, you're not assuming revenue neutrality, so the auctioneer may have to pump in some of his own.
So I don't believe in any of the examples I cited that the auctioneer will ever lose money. It's possible that he may not gain money. So, sorry, if it's the case that he has to pay money to build a bridge, it's definitely possible that the cost of, that what everyone pays you may not cover the cost of the bridge. That's right. Yes. So that's I guess I would consider that as a different direction than this, but those are definitely important problems. Yeah. Okay. Yes.
I'm trying to understand how the revenue problem is different from the welfare problem. Is in the revenue you get to charge anything up to what the welfare is for that person, right? So how's it different?
So the reason it's different is because let's say that my mechanism is just going to charge you whatever you say. Then, like, even let's just say it's just you and me interacting, and I tell you the mechanism is that if you tell me that the item is worth $10 to you, I'm going to charge you $10. Then you're definitely not going to tell me your actual value. You're going to tell me something much lower.
So when the agents were just going to tell you the truth, then you could actually
yes,
charge
it would be
up to
exactly.
what they
That's
want,
correct.
but
It would be exactly the same as
in
welfare.
mechanism setting, you might not be able to charge.
Yes, that's right. And in fact, you have to charge them something less because you want it to be truthful. Right? Okay. Good. Okay. So, so I told you, so the main result is this black box reduction. So it's a polytime reduction from the mechanism design problem for any objective that you want to optimize to the algorithm design problem for that same objective plus virtual welfare. Okay? So what that means is that in this picture, whenever the right-hand side, this algorithm design problem is tractable, then so is the mechanism design problem that's on the left. Okay? And so two facts I wanted to emphasize that this reduction is approximation preserving. So if you have a hard problem to solve on the right, like independent set, that you can't, maybe an example that you could at least approximately solve, if you can approximately solve the algorithmic problem, then you can approximately solve the mechanism design problem, and it's the same ratio. And also, there's no constraints on the types that the agents have to have in order for the reduction to work. So however the types get input to the mechanism design problem, they get passed in the exact same way to the right-hand side for the algorithm problem. Okay? And so one way to...
What are the constraints on the objective O?
So if you're trying to... So let me say this. So if it's in... For the most part, it can be anything. If it's an objective that interacts in a weird way with randomness, then it has to be concave if you're maximizing it, or convex if you're minimizing it. But if it's like if it's an objective that, like you would say, expected makespan might be something like you compute the makespan of this, you compute the makespan of that, and you average them. Then, if it behaves like that with randomness, then it can be anything. Okay, did that? Yeah.
Looks like a reduction on virtual welfare is something that you sort of decide to add in to tell the existing algorithm.
Yes, that's right. So it's definitely possible that maybe adding virtual welfare makes it a much harder problem. That's definitely possible that that might happen. And actually, we'll see an example later where that's the case.
Also, it looks from this as if you run the existing algorithm on that with, it says known agent types. So you have to. So how do you then go back?
So so in this slide, I'm just thinking of this as not pretending that you know the actual agent types, but as an algorithmic problem, imagine that you did know the agent types. That's the one that you have to be able to solve. So
we have a machine that does
yes,
that.
that's right. Yes, that's right. Think of it as you have a machine that solves this problem on the right. You can probe it several times, and that will let you solve the problem on the left. Yes, that's right. That's the right way to think of it.
Is one of the parameters in the polynomial the number of agent types? I mean, when you say polynomial type?
Yes, good. So, so it is the case that the runtime is polynomial in the number of total agent types. So it's different than the number of type profiles. So that would be very bad. So say there are 10 agents, then the number of type profiles would be exponential in 10. So that would be really bad. In some cases, even just the number of agent types is really not good. But in some cases, that's also the best you can hope for. Yeah, so that's a good question. Okay, and so this at the bottom, this is one way to think of this result, is saying that transitioning from honest to strategic input is no harder than adding virtual welfare to the objective. Okay, so maybe adding virtual welfare to the objective, maybe that does make the problem a lot harder, but dealing with strategic agents is no harder than that. Okay? Okay, so now I'm going to tell you a little bit about the tools and techniques that get us here. And so for now, I'm going to say the objective is revenue, and the agents are going to be additive. And just to remind you what that means, there are n items, and agents have values for each item, and their value for a set of items just sums their value for every item in the set. Okay, this is just going to make talking about it a lot cleaner. Okay, so the first thing we have to look at is how should you describe a mechanism? So one observation you can make is that a mechanism is just a function. So it takes as input type profiles, and it outputs a price for all agents, and it outputs a distribution over outcomes. So one way to describe a function is a really explicit description where you just list for every possible input, what is the output? Okay, so I'll call this like a laundry list. So with this description, you can think of a mechanism as a really large dimensional vector that just lists for every possible input and for every possible output what's happening.
Distribution over outcomes, so you're allowed to have a mixed or random mixture?
Yes. So by that I mean the mechanism is allowed to be randomized. So same thing. If I'm trying to build a bridge, then my mechanism could decide with probability 1/2 it builds a bridge here, with probability 1/2 it builds a bridge there, and maybe that lets me do something that I couldn't do with a deterministic mechanism. Okay. So now that we decided we're going to think of mechanisms as vectors, one thing you might ask is, can you write a program that will just optimize over the space of truthful mechanisms?
So is price a deterministic or will it depend on the outcome of the distribution?
Say that again?
So there, like the way it is written, is the price a deterministic?
The price, so for now we'll say it could be deterministic, it could also be a distribution. As far as the agents are concerned, so I didn't explicitly say this, but I'll assume that the agents are risk neutral. So as far as the price is concerned, they don't actually care. Yeah. And let's also say that as far as you're concerned, you're also only concerned with the expectation. So if you want to, you can use randomness. Okay, so the answer is sure. You can definitely write a program that will optimize over the space of truthful mechanisms. But really what this is going to look like is it's going to look really silly. It's going to look like you're writing a program to optimize over all algorithms, and then you're going to throw in a constraint to make sure that the algorithm is truthful. Okay? So what this looks like is you're going to have variables, like I said, to explicitly describe this function. So for all possible inputs and all possible outputs, what's the probability that you choose that output on this input? And for all possible inputs, for all agents, what's the price you pay on that input? Okay? And then you have to constrain that the mechanism is truthful. And I'm not going to write them, but you can write that with linear constraints. And you have to guarantee that the mechanism is feasible. And those are also linear constraints. And so by feasible for this, I just mean that on every output, for every input, we have a variable denoting the probability that an outcome is chosen. These probabilities should sum to 1 in order for this to be a real distribution. So that's all that's going on there. Okay, and now to optimize, you just want to optimize your expected revenue. And I'm also not going to write this, but this is also a linear function. Okay, so I just told you here's a linear program that solves the problem you want. And so what's the problem? The problem is that this is enormous, and there are way too many variables. So what we need is a smaller description. Okay, the description we're going to use is something called reduced forms. Okay, and so the idea is that we really don't need all this information. Okay, so let's just try and keep what's important. So what we're going to do is we're going to make a variable for every agent, for every item, for every type. What's the probability that they get that item when they say this type? And this probability is going to be over the randomness in the mechanism, if there is any, and over the randomness in the other agents choosing their types. Okay? And this pi of t is just going to be the expected price they pay when they say this type. Okay, so now you can also think of this as a polydimensional vector, so it's much smaller, the description. And you want to say that a vector is feasible if it corresponds to an actual mechanism. Okay, so it doesn't have to be a truthful mechanism, but it should be an actual mechanism. So as a picture, what's going on is on the left, we have the space of all mechanisms, and on the right, we have the space of all vectors that at least have the right number of coordinates. And every mechanism induces a reduced form. And so the set of feasible reduced forms is the image of this map, and that's a subspace of the vectors that have the right number of coordinates. Okay, so the first ingredient in the solution is going to be to write a linear program using this compact description instead of the laundry list one. Okay, so the variables you're going to have are this, what I just said, so from the reduced form. You still need to guarantee that the mechanism is truthful. And again, I'm not going to write this, but you can do this with a small number of linear constraints. And now the interesting problem is that it's kind of hard to guarantee that a description is feasible. Okay, so you can't do that with few linear constraints. And the new challenge is how can you tell if a reduced form is feasible? Okay, but you're still maximizing expected revenue, so that part is easy. Okay, so the first ingredient, we wrote a succinct linear program and using the reduced forms. So all we need to do now is find out how to tell if a reduced form is feasible. So that's going to be the next step. Okay, so to help you understand this, I'm going to give an example. So the purpose of this example is 1, just to give you an idea of what it means to say a reduced form is feasible, and 2, to convince you that this is an interesting, non-trivial problem. Okay, so to do that, I'm going to do a really simple example. It's just going to be one item and 2 bidders, and each bidder is going to have 3 types. Furthermore, each bidder's type is going to be chosen uniformly at random. Okay, so here's my reduced form that says that when bidder 1 says his type is A, he should always get the item. If he says his type is B, he should get it with probability 1/2. If he says his type is C, he should never get it. Okay? So let's try and figure out, is this feasible? So the first thing we can look at is definitely whenever A shows up, he has to get the item. So something that we have to do is A has to beat D, E, and F whenever they show up. So we can do this, and now we know that pi of A is equal to 1. So that's good. Also, now that D is losing to A, D has to get the item whenever else he shows up. So that means D has to beat B and C. Okay, but if we do this, then pi of D is going to be equal to 2/3. So that's fine. Another thing we can do is C and F don't want the item at all. So whenever B and F show up, we might as well give the item to B. And whenever C and E show up, we might as well give the item to E. And that gets both of their pi's up to 1/3. And now the last decision we have to make is what should we do if B and E show up? So in order to get pi of B all the way up to 1/2, B would need to win with probability 1/2. And in order to get pi of E all the way up to 5/9, E would need to win with probability 2/3. Okay, and so at this point you can say, well, 1/2 plus 2/3 is larger than 1, so it's clearly not possible to do this. So this reduced form is infeasible. Okay, so what just happened? So we worked out a simple example, and that was already kind of a lot of work. All right, and I want to point out, so like what would have happened is if pi of A wasn't equal to 1, we wouldn't have had a starting point to go through that kind of reasoning. What if there were more than 2 bidders? What if there's more than one item? And what if there are interesting constraints, like maybe a matching on who can get what at the same time? Okay, so hopefully I've convinced you this is a somewhat interesting problem, and what we need is a consistent approach to solve it. So the second ingredient is going to be what's called the equivalence of separation and optimization. And to tell you what this means, I'm going to give you a definition. So a separation oracle for a convex region takes as input some point x, and it's going to output either yes if x is inside your convex region, or it's going to output a violated hyperplane. So how you should think of a violated hyperplane, there's some direction w where x goes further in direction w than any point inside the polytope. And therefore, it's definitely not in the polytope because it goes too far in direction w. Okay? So there's this famous theorem by Kachian in '79 where he showed that if you can get a separation oracle for a convex region, then you can optimize linear functions over that same region. And the algorithm we use is called the ellipsoid algorithm. Okay, so what this means in our context is that we just need a separation oracle for the space of feasible reduced forms, and then we can solve our linear program. Now, what's less known is that the other direction is also true. So in 81, Grochel, Labash, and Shriver, and independently Karp and Papadimitriou showed that if you can optimize linear functions over a convex region, then you can get a separation oracle for that region too. Okay? So a good question to ask, yes?
Do the rules on what is feasible, which could be computationally very complex, require that it still be a convex problem?
Yes, and it's actually always going to be convex. And the reason you can think of that is if it's feasible for me, think of it like this, if it's feasible for me to run one mechanism, and it's feasible for me to run another mechanism, it's feasible for me to run this one with probability 1/2 and this one with probability 1/2. So it will also be feasible, and does that make sense? So it's feasible for me to choose this one.
In the allocation, is what I meant. Like, you can give you can give each person a house, but only one house or something like that. I'm not sure how complicated these rules can be, but those still have to define a convex set.
So those actually don't have to define a convex set. So what I'm saying is that if I look at the probability vector that you get each different house, if it's possible for me to do that, and it's possible for me to give you a different probability vector, then it's also possible for me to give you this one with probability 1/2 and this one with probability 1/2.
So once you project down onto this much smaller dimensional
Yes,
space,
that's right.
you get a convex set.
Yes, you
even though
immediately
didn't
get
have one
convexity.
up.
Yes, that's right. That's right. Okay. So a good question to ask is, why is this second theorem I showed you, why is this ever useful? Like, who uses separation oracles for anything other than optimizing linear functions? Okay. And so the answer is that the most common usage is if you want to optimize a linear function over the intersection of two convex regions. And in this case, just being able to optimize a linear function over one doesn't immediately tell you anything useful about optimizing that same function over the intersection of two regions, unless you use this reduction. Okay? And so actually this is this application is what gave the first polytime algorithm for submodular minimization. And there are other uses of this, and one of them will come up later in the talk too. Okay. So the second ingredient, which was not our contribution, is the equivalence of separation and optimization, which says that if you have an optimization algorithm for this region, then you can get a separation oracle. So all we need to do is be able to optimize over this region. Okay. And I'm actually going to skip the details on this, but I'll tell you that one thing we did show is that if you can optimize virtual welfare as an algorithmic problem, then you can optimize linear functions over this region. Okay, and I said I'm going to skip the details, but I'll say that one way to interpret this is that it's a stronger version of the equivalence of separation and optimization, but specifically for this mechanism design application. So it's not like a general tool. Okay. So now when you combine these three ingredients together, this says that if you have a polytime algorithm that can optimize virtual welfare, you can go back through ingredient 3, then 2, then 1, and that will give you a polytime algorithm to find the optimal reduced form. Okay? So something is still missing, and that's I told you that there's an algorithm to find the optimal reduced form, but a reduced form is not actually an auction, or it's not a mechanism, because I threw away a lot of information. So what I need is I need an actual mechanism that can take as input a profile of types and output what to do. It can't just be the case that everyone shows up and says they're types, and then I say this is the reduced form of what I'm trying to do. Right? I actually need to do something. Okay? And so this is another use of separation oracles, which says that if I give you a separation oracle for a convex region and a point inside that region, then I can decompose that point into a convex combination of corners. Okay, of extreme points of that region. And the reason that that's useful is because we're able to show the following, that any reduced form that is a corner of the feasible region has a really simple form and can be implemented as a mechanism really easily. And it's just by maximizing virtual welfare on every profile. So what that means is you should think of every corner modifies the input in a different way, but then it just maximizes welfare at the end of the day. Okay, so the corners are really simple mechanisms. So what that means is to implement any feasible reduced form. First, you use a separation oracle to write it as a convex combination of corners, and then you implement that corner. And the corner just modifies the input and then runs an algorithm that maximizes welfare. Okay?
Corner, this convex set, is it actually a polytope or?
So in most examples that you would think of, it is a polytope. If it's not a polytope and it's just a convex region, then by corner I mean like an extreme point that's, not, what's the word I'm looking for? Yes, that's right. That's correct. That's the right way to put it. Yeah.
What do you mean by modifying the input at a corner? Do you mean that different corners have different virtual values?
Yes, that's what I mean. Yeah. Okay. So now this is a last ingredient. And so with all four of these together, this means that you can find and implement the mechanism that optimizes revenue in polytime as long as you have black box access to an optimal algorithm for virtual welfare. Okay. So what I just proved was the theorem that I just read, which was for revenue, for additive bidders, and for exact optimization algorithms. What I promised you at the beginning was the following more general theorem that said any objective you want, and it preserves approximation, and the agents can have any types you want, not just additive. Okay? And so the proof uses the same four ingredients plus a little bit extra that I'll go through now. Okay? So the missing ingredients, I need to tell you how to deal with approximation. I need to tell you how to let the agent's types not be additive. And I need to tell you how to change the objective from revenue to something else. And I'll give a one-slide overview on each now. So for approximation, so recall this theorem that I told you earlier, which is that if you can optimize linear functions, then you can get a separation oracle. And a reasonable question to ask is what happens if you use exactly the same approach, but I just start with an approximately optimal, or an approximation algorithm instead. Okay? And so you can call the output of this, we call it a weird separation oracle. The reason we call it that is because it is an algorithm that sometimes says yes, and it sometimes outputs hyperplanes, but it's not really a separation oracle. And the reason for that is that it can have this really weird behavior where it's possible for it to accept the point x and accept the point y, but reject every convex combination of x and y. Okay? Whereas if the region was actually convex, not only should it accept some of these points, it should accept all of these points. Okay? So that's why we call it weird. Okay? But an informal statement of the theorem that we show that says if you can approximately optimize linear functions over a convex region, then you get some meaningful notion of an approximate separation oracle for that same region. Okay, and the exact definition of what I mean by a meaningful notion is a little technical, so I didn't write it. Okay, but an overview of what happens is we show that the same algorithm that was used in the original reduction works directly. And the hard part is we have to understand what happens if you run the ellipsoid algorithm like over a non-convex region, like what will happen. Okay. So the idea is that if you have a real separation oracle, then the set of points that it accepts are going to be a convex region. And so this weird separation oracle doesn't have that property. So it's going to accept some points, and those points are going to form a set. And this set may not be convex, and it might not even be connected. So it can be a really weird set.
So this approximate optimization problem for each query gives some consistent answer.
Yes, for each query it gives a consistent answer, but it's in some sense not consistent with any single convex region. That's right. So it could be the case that like in one direction it says you can go very far, and in this perturbing that direction just a little bit, it says you can barely go anywhere. So it's possible that that will happen. Okay, so that's how you deal with approximation, is you need to use this stronger version of the reduction. Okay, so now how you deal with, so for arbitrary types, let me first try and ask, so what goes wrong as you move beyond additive bidders? Yeah.
So in this approximation, you would still just aim for the worst one, right? Like you said. So for example, when you said for different inputs, it gives, in some sense, an approximation in a different fashion.
Yes, that's right. So yes, the worst one. So, but you guarantee that in every direction it does at least half as well as the optimal, then that's what you're targeting.
Even
Yes.
Actually, on somehow the kind
Yes.
of input you're probing, it was doing the approximation algorithm was somehow
Yes.
working well, but you were still late for
That's
the
right.
first
So
one.
so I don't know how to exploit that property. That's right. So even if it did well in every direction except for one, I wouldn't know how to exploit it. Yeah. Okay. So let me now ask, so what's the problem as you try to move beyond additive bidders? And the issue is that this reduced form I was using is completely useless, and here's why. So say there's just one bidder and there's two items. You should think of the items as a left shoe and a right shoe. Okay, so your value for both shoes together is $1, but your value for just one shoe or getting nothing is 0. Okay, so that's an example of a bidder that's not additive. Oops. And in one auction, maybe I give you both shoes with probability 1/2 or nothing with probability 1/2. Or in a second auction, you just get a single shoe uniformly at random. And these two auctions have the same reduced form, but your value for them is really different. Okay, so the problem, right, so that's the problem, and how do we deal with it? So we use a different description of the auction that's really implicit. Okay, so we'll use, sometimes you can think of this as like a swap value. So we're just going to explicitly get at what is your expected value if your real type is t, but you choose to say t prime instead. Okay, and then we store this for all pairs of types. Okay, so I'm not actually storing any information about the auction other than directly how happy does it make certain types for reporting certain other types. Okay, so that's how you deal with arbitrary types. And now I'll tell you how to deal with arbitrary objectives. So what you want to ask is, what makes revenue special for this approach? And the answer is that expected revenue is a linear function of the reduced form or the implicit form. Okay, whereas most other objectives aren't. So for instance, welfare is, but Makespan isn't. Okay, and so the issue is that if I just give you the implicit form of a mechanism, there is no way you can possibly hope to compute the Makespan. Okay, so the solution is we're just going to add another variable that stores this value directly. Okay, so we'll take the implicit form and we'll add one more variable, and that's just going to store the expected value of, say, Makespan. Okay, so this definitely makes writing the LP easier. And the issue is that it may make determining feasibility a lot harder. Okay, because now I have to determine, is it feasible for me to make, you this happy when you say this other type, and for me to do so in a way that gets Makespan exactly 5 or something. So now this is a much harder problem to deal with. Okay, so just to recap, so this new implicit form is going to have these 3 components. The first is going to be this swap value, which says if your real type is t, what's your value when you say t prime? It's also going to store the expected price that everyone pays. And it's also going to store the expected value of the objective when you use this mechanism. Okay? Okay, so now let me go back to these 4 ingredients and tell you how they change when you want to make these generalizations. Okay, so instead of using the reduced form to handle arbitrary types and objectives, we're just going to use this implicit form that I told you. So all we're doing is changing the variables, and as far as the LP is concerned, nothing interesting happens. Okay. So to handle approximation, we have to use this stronger approximation preserving version of the equivalence of separation and optimization. But once we do that, that's the only change we need to make. Okay, and so for this third ingredient, optimizing virtual welfare no longer lets us optimize over the space of implicit forms because we added this component for O. But it turns out that adding this extra variable just causes the problem that you need to solve to change. So if you want to optimize over the space of implicit forms, you just need to be able, to optimize O plus virtual welfare. Okay, so that's how it changes, and that's where this problem of O plus virtual welfare comes from. Okay, and for the last ingredient, because we no longer have an actual separation oracle, we can't use that decomposition algorithm that I told you about before. So instead, we have to use a property of the approximation preserving reduction, so this decomposition will just come immediately out of using the technique. Okay, so now I've shown this more general version of the theorem, which says that you can find and implement an approximately optimal mechanism for any objective, for arbitrary agent types in poly time, as long as you have black box access to an approximately optimal algorithm for that same objective plus virtual welfare. Okay? Okay, so now let me tell you about some quick applications. So the first application is, not surprisingly, for revenue. Okay, so in 1981, in Meyerson's seminal paper, he showed the following structural result about auctions. We said that the revenue optimal auction in single-dimensional settings is a virtual welfare maximizer. And a major open question since then is, what does a revenue optimal auction look like beyond single-dimensional settings? So even for additive, we don't know anything, and definitely beyond additive, we really don't know anything. Okay? So what I showed you in this talk is that no matter what the agent types look like, the revenue optimal auction is a distribution over virtual welfare maximizers. Okay? So it's not quite as simple as Meyerson's, but it's not like super far from that. It's definitely more than what we knew before. Okay? So a note is that Meyerson also showed the other direction, which is that any approximately optimal mechanism necessarily approximately maximizes virtual welfare as an algorithm. Okay? And so we can show something like this too in our setting, which I'm going to say now. Okay? So what we show is that for revenue, this reduction actually holds both ways. So what I mean by that is if I gave you an algorithm that could find the optimal truthful mechanism, or even an approximately optimal truthful mechanism, you could turn that into an algorithm that can approximately maximize virtual welfare algorithmically. Okay? And so the proof of this I'm not going to talk about at all, but it has nothing to do with the geometric techniques that you saw in the rest of the talk. Okay? So an encouraging corollary of this is that in this setting, that means that maximizing virtual welfare is in some sense the right way to maximize revenue, because you can't avoid doing it. If you had an algorithm that can maximize revenue, you would also have an algorithm that maximizes virtual welfare. Okay? So an evil corollary of this is that we're able to show as a corollary that it's NP hard to truthfully approximate revenue within any polynomial factor, even for a single monotone submodular bidder. Okay? And if you don't know what those terms mean, monotone just means that as he gets more items, he gets happier. And submodular means he gets diminishing marginal returns from adding more and more items. Okay? So as a second application, I'll talk about Makespan. Okay? So, if you remember, there was this guy who was trying to schedule jobs, and now he's a little bit excited because he just has to design algorithms for Makespan plus virtual welfare. So let me give you a specific problem. So you want to truthfully minimize Makespan on unrelated machines. And so what that problem sounds like is there are n different jobs and m machines, and processing job I on machine j takes time pij. And this is private knowledge to the machines. Okay, so you don't know how long it takes to process any job on any machine, but the machines do. And I want to point out this is the original problem that was studied in this seminal paper of Nissan and Ronen. Okay, so in this talk, I told you that this reduces to an algorithm design problem for minimizing Makespan plus virtual welfare. Okay, so one way that you can interpret this problem is that processing job I on machine j takes some processing time, and it also costs some monetary value. Okay, so think of it as you have to pay the machine to process a job, and it's also going to take them some time. And your goal is to find a schedule that minimizes the time to process the last job, so that's the Makespan component, plus the total monetary cost of processing all jobs, and that corresponds to the virtual welfare component. So think of it as you only care about the time it takes to finish the last job, but you also care about all the money you spend. Okay? Now what kind of sucks is that this problem is NP hard to approximate within any finite factor. So not just within a constant factor, it's NP hard to determine if the answer is positive or negative. Okay? So I just spent a half hour telling you about this really general reduction, and now I gave you an example of a problem that says we can reduce a problem we don't know how to solve to a problem that's impossible to solve. Okay? So you should ask if, is this not the right approach? Okay? But the answer is we can still accommodate this, but we need to improve the reduction a little bit. Okay, so I'm going to give you one more definition, and I promise this will be the last definition of the talk. So we'll say that an algorithm is an alpha-beta approximation if the output satisfies this following inequality. And how you should interpret this is that if beta was equal to 1, this would be a normal alpha approximation. Okay? But by letting beta be something less than 1, this is letting you cheat a little bit. So it's letting you discount the objective by some factor before you compare to alpha times the optimum. Okay? And so what we're able to show is that if you have a polytime alpha beta approximation algorithm for optimizing your objective plus virtual welfare, then you can turn that into a polytime alpha over beta approximate mechanism for the objective. Okay, so that means having beta not equal to 1 just causes you to have to sacrifice another factor of beta in your approximation ratio. Okay, and so I'm also not going to give any details of the proof, but I'll say that it's by basically extending this equivalence of separation and optimization to accommodate some geometric notion of this kind of approximation. Okay, now what's really cool is that for Makespan, this problem was actually studied 20 years ago, and Schmois and Tardos showed that there is a polytime 1/1/2 approximation algorithm for minimizing Makespan plus virtual welfare. So what that means is that when you plug that back into our reduction, you can get an actual 2 approximation for a truthful Makespan minimization on unrelated racines in this Bayesian setting. And I want to point out that first, that matches the guarantee of the best known algorithm. So even if we didn't have any strategic input, on honest input, we don't know how to do better than a 2 approximation. And also, if you think this is a really important problem, then this is the first general Bayesian setting constant factor approximation. Okay? So in conclusion, so we studied this general question motivated by Nissan and Ronin. It said, how much harder is it to solve problems on strategic input than honest input? And we studied it through this specific open question, which is when are there black box reductions from mechanism to algorithm design? Okay, and so what I showed you in this talk is that for all objectives in a Bayesian setting, there is a black box reduction from mechanism to algorithm design as long as you perturb the objective. Okay, and so one way to think of that, like I said before, is that transitioning from honest to strategic input computationally is no harder than adding virtual welfare to your objective. Something we did was we extended this equivalence of separation and optimization framework to accommodate both traditional approximation and alpha beta approximations. And I also showed you that this reduction is, or I didn't show you, I told you that this reduction is tight for revenue. Okay, and so what that means is that maximizing revenue in this setting is exactly as hard as optimizing virtual welfare. Okay? And something else, if you care about structure, I showed you that the optimal mechanism has manageable form, which means that how you can implement it is you randomly sample a corner, and then you run the corresponding virtual objective maximizer, where modifying the input is going to depend on which corner. Okay, so that's all I'm going to say about that, and I'm just going to really briefly talk about 2 other things that I've done. Okay, so changing gears, profit inequalities are kind of a fundamental problem in online algorithms and optimal stopping. And it turns out that this actually has strong applications in mechanism design. Okay, so I'll define the problem. So the offline input to this problem is a list of distributions. And what happens online is that random variables are sampled 1 at a time from each distribution. They're revealed to you, and as soon as it's revealed, you have to immediately decide do you accept or reject. Okay? If you accept, then you get reward equal to the random variable you just saw, and the game stops. If you reject, you throw it away forever, and then the game keeps going. And your goal is to maximize your expected reward. Okay? So if you were a prophet who knew the future, so this is where the term profit inequality comes from, you'd always get the maximum element. And the question that you want to ask is, if you were a gambler who didn't, how well can you do? And so there's a seminal result that says in this setting, there is a strategy for the gambler that guarantees him half the expected reward of the prophet. Okay, and this is the best you can possibly hope to do. Okay, and so recently people have been trying to study what happens if the gambler has multiple choices. So I'm going to change the offline input of the problem to be also a list of distributions, and there are going to be some feasibility constraints that say what elements you can simultaneously accept. The elements are still revealed one at a time, and you still have to decide online whether to accept or reject. Now the difference is when you accept an element, the game doesn't immediately stop. It just gets added to your accepted set of elements. And the catch is that at all times, your accepted set has to be feasible. Okay, so what you lose by accepting something is it'll prohibit you from accepting some other things in the future. Your goal is still to maximize your expected reward. It's still the case that if you were a prophet, you would always choose the max weight feasible set. And so what I showed with Bobby Kleinberg is that if the feasibility constraints are a matroid, then there exists a strategy for the gambler, also guaranteeing him half the expected reward of the prophet. Okay, and this is the best possible because it's the best possible even for the single choice problem. Okay, and also recently with Pablo Azar, we showed that there exist asymptotically optimal strategies for the gambler that only require a single sample from the distributions. So he doesn't actually need to know the distributions outright. One sample is enough. And this is for several special cases of matroids, but not actually for matroids in general.
When you say is a matroid, you mean the independent sets?
I mean the independent sets form a matroid. Yes, that's right. Okay, and so the last thing I'm going to talk about is auctions for everyday people. And so the motivation for this is that the mechanisms that I just finished describing to you, I would consider them manageable, but I would not call them simple. So what I mean by that is that the FCC could run this mechanism as a spectrum auction. They're definitely capable of doing that. But what I also mean is that I could not run that mechanism to sell my Pokemon cards. Okay? So there is some bad news with respect to this problem, which is that even in ridiculously simple settings, the unique optimal mechanism can be very complicated. So in particular, Hart and Rennie showed that even if there's just one buyer and two items, and his value for each item is drawn IID from a distribution of support 3, then the unique optimal mechanism is already really complicated. Okay? So the good news is this doesn't rule out simple and approximately optimal mechanisms. Okay? But we do have to start kind of small trying to approach this. Okay? So that's a good question. For this specific example, so I would say one measure of complicatedness is if it uses a lot of randomness. And another measure might be, I guess it's kind of a fuzzy notion of complicated in that it doesn't look like it looks weird. So what their mechanism, I'll just tell you what the optimal one is for this setting. Is that it offers the buyer like the following 4 options. He can either pay a lot of money and get either item deterministically, so with probability 1, or he can pay less money and get both of them at the same time, or he can pay less money and buy a lottery ticket for one item that gives him the item with probability 1/2. So he can buy a lottery ticket, walk over to another counter, hand them the lottery ticket, and they'll flip a coin. Maybe they'll give him the item, maybe they'll give him nothing. And he can buy one of these for either item. Okay? Does that? So, I don't know. I would say that's something that to me seems complicated. Okay. So the model is there's just going to be one additive buyer, one seller, and n items. The buyer's value for each item is going to be sampled independently. Here are 2 simple ways you can sell the items. One is you just sell them all separately. Okay, so I just put one price on each item, you walk in, you buy whatever you want, and then you leave. So think of that as probably any time you've ever bought something was probably like that. Another simple thing you can do is put them all together into one big bundle and put a price on it. Say you can buy everything or you can buy nothing. Okay? And so there's bad news even for this, which is that there do exist instances where selling everything separately does really bad compared to the optimal. And there are instances where selling everything together does really bad compared to the optimal. So what we showed with Moshe Babayov, Nicola Moilica, and Brendan Lucier is that for all instances, one of them does good though. Okay, so one of them is always a constant factor, even though there are instances where, so even though for both of them, there are instances where they both suck. Okay, so as a fuzzy corollary of this, this means if you sold anything on eBay recently, you probably did it in a way that is provably approximately optimal. Okay?
So one question here, the seller decides which of these to apply.
Yes,
there's
correct.
another option where the seller would tell the buyer, well, you could either buy a
That's
bundle
true.
or buy them separately.
Yes. That's
So
right.
is it,
No, so this is the seller beforehand decides which one do I think will make me more money, and then he uses this one. And it's actually, it's very easy for the seller to tell which one will make him more money.
but what if he does this thing of giving the buyer the option? Is that known to be bad?
Okay, so I guess I would say, by this result, kind of trivially, that would have to be good, because you can always, you can always just set the price of one of them to be infinite or something, and that, right? Or I could set it to be something so high that you will never actually choose it. Or if you do choose it, then I'm making a ton of money, so it's only good, right? So that would be maybe that's a better way to state it, which is you can just sell either the options of buy everything separately, or maybe for this much higher price, you can buy every. Sorry. Or maybe.
Lower than the sum of the price.
Yeah, yeah. Unless you don't want him to choose that option, because really you want to sell everything separately, then. But yes, that's true. Okay, and so that's everything I have. Thanks a lot for listening.
I guess from initially you just compared the result to Meyerson result, but that was a deterministic mechanism.
So it's not comparing to Meyerson's, it's comparing to whatever the best, really complicated thing you could possibly do. So you're talking about for the last result? This one?
No. The main part of the talk. I was just trying to say over there, like for example, in Meyerson's setting, it's not clear right away that you do get Meyerson's result now.
Yes, that's true. So in the main result, I'm not comparing to the optimal deterministic mechanism. I'm comparing to the actual optimal, the best thing you could do for any complicated truthful mechanism. That's what we're comparing to. So it could use randomness. It could, do something really crazy.
But can you say in some places that randomness is not necessary? For example,
So not for any new settings, we can't. So so one thing that we did try is we tried to say, now that we know all of this, could we rederive Meyerson's result? And the answer is yes, and you could give a geometric proof of that instead of using calculus. It's not clear that that's really simpler, but you could. But we didn't, I think that's a great question, but that's not something that we've been successfully able to look at.
You explained your benchmark in the beginning as you're comparing to the optimal truthful mechanism.
Yes.
Now, again, in some special settings, requiring truthfulness doesn't hurt, but in some it does.
Mm-hmm.
So what? I guess if the benchmark was the best, or maybe a natural benchmark is the seller could say, I don't care necessarily about truthfulness. I just want to do the best. So I know that saying something like GSP won't motivate people to tell the truth, but I'll still be better off.
That's right. So you're just saying, what if there's a higher benchmark, which is the best you could do with an algorithm? So I guess let me answer that first, and then maybe there's a second thing you were trying to get at. So the first is that's a better benchmark, and we do know in some settings, like for welfare, you can achieve that benchmark. And as far as I know, actually, there are not a lot of settings where we know that you can't. For Bayesian incentive compatibility, if you want dominant strategy truthfulness, then there are some settings where we know that you can't do as well with a truthful mechanism as an algorithm. And so one useful thing, I think, is that, so we are working to actually code up these algorithms and implement them. So with this, you could actually run some experiments and see, try and get some intuition as to, say, for Makespan, do you think that the gap should be a constant factor? Should there be any gap at all? Or should it be enormous? And so we haven't finished coding up the implementation, so we haven't done that. But and honestly, I don't have any intuition into that. Maybe another interpretation of your question would be what if you just run something that's not truthful and see what happens? How much revenue will you get? And so, so there is this thing called the revelation principle that says that, well, if the bidders are actually behaving strategically, then you could make just as much revenue by behaving strategically for them via a truthful mechanism, right? So, it's unclear that bidders actually do behave strategically. If you give them more options. But I think it would be nice to have some kind of robustness argument that says that, like it's in everyone's interest to tell the truth, so they should tell the truth, and you make this much money when they tell the truth. Whereas if you just kind of let them do whatever they want and you have no guarantee on what they're going to do, then it's much harder to get any kind of guarantee.
That I understand only vaguely was when you have solved the problem in the low-dimensional space and you're trying to find an action that bodies that. And so in a fuzzy way, I gather that in the first instance where everything was additive, that you sort of map the problem to want to find it separating points, and because these extreme points have nice properties, then it works. But I didn't see, is it the same when you go to the non-additive case and you replace these representations by just sort of expected values of what happens to
Yes. Yeah. So, right. So first, let me tell you. So for revenue, when you go to this more general space with this swap value description instead of the other description, then it's still true that the extreme points have this nice property, which is that they are still virtual welfare maximizers. But what virtual welfare means gets more complicated as you let the types become more complicated. So for instance, when you start with additive bidders, the virtual welfare maximization problem is still going to be on additive bidders. If you start with something like submodular bidders, so let's say that all of your bidders have submodular valuation functions, then the virtual welfare problem might ask you to maximize welfare when they have like the difference of two submodular functions, which could get much more complicated than just a submodular function. So let me say, as a characterization result, it's still true that all of the extreme points are virtual welfare maximizers. As you go to this more complicated description, then what it means to be able to maximize virtual welfare gets more complicated and harder. There's a second thing, which is, so I told you that if you don't have a real separation oracle, so if you just have this fuzzy approximate version, you can't run this algorithm to even find the corners to begin with. And so what happens is that let me say it like this. So whenever you use this approximate equivalence, whenever you say that a point is feasible, you can actually explicitly find a convex combinations of points that give you this one, such that you can find that point just by running your algorithm in a certain direction. So so what that means is that if I have an approximation algorithm and I want to implement some mechanism, I can do it by randomly choosing a virtual transformation and then running whatever algorithm I used to find it. So if I had an approximation algorithm, it'll be that same approximation algorithm. I don't know if that was too.
Not sure.
Okay.
We'll have to continue.
Yeah.